Okay, neighbor joining algorithm has the same structure as the UPGMA in terms of the general algorithm structure. We are going to, at each iteration, we are going to combine two objects, two nodes in the current matrix, and we are going to set up these three weights and find, and after that, we need a way to update the new matrix. After we combine, for example, B and C, when we put BC to get in this matrix, we need to find out these things. So let's see. Let me get a new slide here. All right, so here we have two objects. First, we need to decide which two objects to combine. That's going to be different from UPGMA. We're not going to only select the closest nodes, closest objects, but we will have a different criteria. We will want to have closest objects which are far as possible from the rest. So we want, in order to combine two clusters, we will have these two criteria: being close to each other and being far away from the rest. So we will combine these two things into a single numerical measure and uh, choose the pair of objects with the property that with this maximum or minimum base, depending on what this measure is going to show us. We'll see being far away from the rest and being close to each other. How are we going to represent that? We'll see. So that's one thing that is different. When we're combining objects, we are not just looking at closeness. We want this I and j to be as far as possible from the rest of the objects. Okay, so we will compute some other measure for I and j for each of these objects. Then after that, when we combine them into this ij, the other thing that we need to figure out, as UPGMA did, was to find what is the distance of I to ij and what is the distance of j to ij. So we need to figure out what these x and y are. Okay, so in UPGMA, this was just divided equally among the nodes. So this was we divide equally. So here in neighbor joining, they will be decided with a formula differently. Another thing is, in order to update the matrix, this ij, what is the distance of ij to some other node k that is in the matrix? Okay, so this is for updating the matrix. Update matrix. So set edge weights, So setting the edge weight. So at each iteration, decide who to combine. Decide which pair to combine. Which pair to combine. So at each iteration, this is the general structure of an iteration. We do these things in this order. These two may maybe change, but the first thing we do is we decide which pair to combine. We want close and far away from the rest. Far away from the rest. And then we are going to decide on these things, and we are going to decide on these things. So these will be different. Each of these steps are different from UPGMA, and let's see how we do that. First, I will first, before we decide on which pair to choose to combine, I will derive the formulas for these three equations: the distance of I to ij, the distance of j to ij, and the distance of the combined ij to the remaining nodes. So there will be some formulas. The entire algorithm is indicated on a single slide on the slides, but I will just instead of memorizing all these formulas on those slides, I'm going to show you a way to derive these, and then we will go over that algorithm. So all these distances, neighbor joining algorithm makes use of the three distances, distances on three paths to compute these things. For example, if I have, in order to, let's start with this simple one first. What is the distance of ij, sorry, the combined node to some node k, okay? So imagine we have combined I and j together into this node ij. And for a particular node k, we want to figure out what this value is. Okay, this is what we want to find out. Now, I'm going to label these three branches here. I'm going to label them x, y, and z. Okay. Now, if these were on a tree, in order to find the distance of ij, this entire cluster, to some k, all I need to know is what is this. I need to figure out what z is. But let's see whether it's possible to find z by using three individual distances. What are those three individual distances? The distance of I to k. If these were individual objects, I would have, in my current matrix actually, I have the distance from I to k, right? I have the distance from j to k. I have that one as well. And I have also the distance between I and j. So these are, in the current iteration, I have these distances. These are in my distance matrix. What is the distance between I and k? What is the distance between j and k? What is the distance between I and j? I have these in my matrix. And let's write them in terms of these three distances here. What is I plus k? It's x plus z, right? What is jk? It's y plus z. And what is ij? It's x plus y. Now, here's what I'm going to do. If I subtract ij from these two, I mean, this is ik and jk. So if I get rid of, because at this moment I don't know what x and y is, all right? I don't know what x and y is at this moment. Instead of finding x and y, I can still find what z is. I can write z in terms of these three values, right? If I multiply this with -1, which means that if I subtract dij from a summation of these two things, right, basically distance between ik, I'm going to just use subscript to indicate them, distance between jk, and subtract from it the distance between ij. Okay, if I look at this, what is this? X plus z plus y plus z minus x minus y. So these x's and y's cancel out. So this here is basically 2z, right? If I divide this by 2, what will I get? I will get z, which is the distance between ij, the distance between ij and k. Okay, so this is this formula that you see on the slide. Let me go to that last slide here. Not the last, this one. You see this, the first formula, the distance between k and ij is this formula here. This formula is driven from what I had written here. The distance between ik, jk minus dij. If you do that and divide it by 2, you get z, which is the distance between ij and k. Okay, so instead of just memorizing the formula, if you just remember how we anyway, if you have the exam, it's going to be open book anyway, so there's no memorization anyway. But finding how these formulas came about is a good way to learn and know the algorithm as well. So neighbor joining algorithm is mainly constructed on 3 paths. So it's these formulas that you see on the slide are coming from considering these 3 paths. Now, here's the other formula that I'm going to show you. By the way, if you have any questions at any time, please feel free to interrupt me and ask your questions. Now, the other thing is, what is this x and y going to be? That's something difficult, right? Because this let's get back to black color. So I have this ij, I, and j. So how do you distribute the distance between ij? So I already have my dij. So the distance between dij, which is x plus y, how do you distribute the entire total distance between I and j into x and y? Here, UPGMA was just dividing x is equal to y. It was just dividing it into 2. Now what we're going to do is we're going to consider all of the distances to all the other objects in the. So for example, let's call this K1, K2, K3, K4. Okay, and let's call these, for example, Z1, Z2, Z3, Z4, and it may go all the way to, if you have n objects at this moment, there will be actually, how many of them are going to be here? There will be n minus 2 of them are going to be here, right? N minus 2 z's are going to be here. Okay, I'm just going to now write an equation here, which is one of the formulas that we're going to have. Let's look at the summation of all the distances from I to the rest. For example, what is the distance from I to j, I to k1, I to k2? So it's, if you write those up, so what you're going to have is x plus y is the distance from this one, and then you're going to have x plus z1, x plus z2, and all the way to x plus zn minus 2. Okay, why is this n minus 2? Because in my current iteration, I assume I have n objects in total. So one of the objects is I, the other is this j. So the remaining number of objects is n minus 2. Therefore, the total number of objects that I'm clustering at this iteration is n. 2 of them are here, n minus 2 of them are here. Now, if you take a look at this, if I call the entire summation z1 to zn minus 2 this capital Z, if I call them this capital Z, what we are going to see here is that I have one y here, and I have one x here, and so x plus y, and I have n minus 2 x's, n minus 2 other x's here, and plus a big Z. Okay, so this is the distance of I to all the other, the summation of the distance of I to all the remaining others. If I do the same thing, so this is from I's perspective. If I do the same thing from the J's perspective, I'm again going to have an x plus y, all right? And this time I'm going to have n minus 2 y's plus the same capital Z. Okay, so the x plus y, again, this is like y plus x, then y plus z1, y plus z2, y plus z3, n minus 2 of such things, and these are the z's. Look at these two equations. What there are three things that are common. This x, y, and z are common in these two equations. If I have a way, so if you look at these things, you have something that tells you what x plus y is, all right? If you want to have another equation that is going to tell you, for example, if you say that x minus y is equal to something, if you have a way to, if this is some numerical value, some constant, if x minus y is equal to this constant and x plus y is equal to this constant, this numerical value that you know, then you can figure out two equations, two unknowns, you can find out what x and y is, right? So here, if you look at these two equations from i's perspective and j's perspective, just look at these two things. I have named them. I didn't give a name to these yet, these summations, but I will give them a name to them in such a way that the difference of these two things is going to give me x minus y. So if I, for example, if you want to subtract the second equation from the first one, what you will end up is n minus 2x minus n minus 2y, right? You have, if you subtract the second term from the first term, these xy's, they cancel, they're the same. These z's, they're exactly the same z's, they cancel out each other, so these go away. The only remaining thing here is n minus 2y, and you just take it like this. So if you want to make this x minus y, what do you need to do? You need to, if you divide the entire thing, if these entire terms, each of them were initially divided by n minus 2. Sorry, not n divided, n minus 2. What would happen was, they would be, for example, x divided by n minus 2, they will be more complicated terms. These will be x divided by n minus 2, y divided by n minus 2, and this capital Z divided by n minus 2. But they're the exact same complicated things in the other term, so they still cancel. Okay, so they still cancel out if I divide this entire term by n minus 2. Now, but the good thing is that what I have here, if I define the terms like this one here gives me directly x minus y. Okay, because these n minus 2 cancel out, and I get myself x minus y. And this formula that you see here is the first thing that neighbor joining does in the first top of the slide. Here it says, look at this, define ui as the distance of I to the remaining nodes divided by n minus 2. So this n minus 2, because since you know now the derivation, this n minus 2 is no longer a mystery. Because if you think about it, if you just look at this equation, it's really simple. It's the distance of I to the remaining, all of the remaining nodes in the graph. And it seems kind of an average, but it's not exactly the average. If you want, if this denominator was n minus 1, it would be the exact average, right? If you divide the summation of n minus 1 terms, by the way, in the summation, there are exactly n minus 1 terms, because the distance of a particular node I to all the other remaining ones, there are n minus 1 other remaining nodes in the in our matrix. That's summation. So you sum here n minus 1 items. If you divided them by n minus 1, it would be the average, but you divide it by n minus 2. So why don't we directly get the average distance of I to all of the nodes? We divide it by n minus 2. The reason is on this derivation. If we divide this by n minus 2, it would nicely give me x minus 1 y. If I divide this by n minus 1, this is by the way, that ui, this is uj, that is defined on the slide. So ui minus uj, if you divide the entire terms by n minus 2 like this, nicely gives me x minus y. If you didn't divide this with n minus 2, it will still give you, it will still be possible to get a second equation and solve the system of linear equations, but it will be a more complicated mathematical term. It will be like this: n minus 1 divided by n minus, no, sorry, it will be like n minus 2 divided by n minus 1 x minus y. It will be like this. The difference between ui and uj will have this constant term in front of it. It will not be this nice x minus y. So you will have your second equation will have this constant term in it. So you will have to multiply it with, in order to cancel these out, to add these two equations directly to solve this system of linear equations of two unknowns, you will have to multiply it with some constant. So it will, it's doable. I mean, if you're programming it, it doesn't matter actually to multiply it with just numbers. It's really easy to do, but it's simpler if if you're doing it by hand. Having an equation that gives you x minus y directly is much simpler, right? Because if you add these two up, y's directly cancel out, you get 2x, which means that dij plus ui minus uj, look at this, ui minus uj gives you x minus y. So if you add these two equations up, you get 2x. If you divide this by 2, you get yourself x. Really easy. And that's exactly the same thing in this formula. ui minus uj plus the distance between I and j. Add these up. So this is x plus y. This gives you x minus y directly. So which gives you, if you add these up, you get 2x. Divide by 2, you get your x nicely. So this nice equation with no n minus 2 divided by n minus 1 somewhere in it is possible due to the fact that we define ui's to be like this. And the reason we divide by n minus 2 again is coming from this derivation to make our life easier. This is just n minus 2 is just a constant, by the way. It doesn't, when we are deciding which nodes to combine, each of those values are going to be divided by n minus 2. So it's like a constant we are dividing this summation. So it doesn't affect it that much. It affects basically what you divide this ui, basically affects how much value you give to the closeness and to being far away. But we give like equal value to all of them by doing this. Okay, so the reason we define ui to be, this ui is like a measure that tells you how far away the node I is to the remaining nodes. For example, when ui is large, it means that if for a particular node I, if you get a large value of ui, it means that node I is far away from the rest of the objects. So when you're trying to find a pair of objects to combine, we want this dij minus ui minus uj. So this is not this formula, this is something else. Look at this measure. What does this tell you? Close to each other? By selecting a pair of objects in which this value is smallest, means that you're looking for pairs of objects which are close to each other. Dij is as small as possible, and ui and uj are as large as possible. When ui and uj are large, it means that they are far away from the rest of the network. So if this is your fitness, or not fitness, let's call it a measure of closeness, or measure of agglomeration. So this is agglomerative clustering, so I can use this fancy term, agglomeration. how they agglunate to each other, as what is their tendency to stick to each other. Their tendency to stick to each other is given by this measure, by saying that dij should be as small as possible and they should be as far away as possible from the rest. So this is basically what we compute for every node. At the beginning of every iteration, we compute ui and uj for all of the nodes one by one. So this is computed from scratch at every iteration for new nodes, because n is changing at every iteration. So this actually, for all of the nodes, ui and uj are computed from scratch. That's why neighbor joining is more time consuming compared to UPGMA, because at the beginning of every iteration, you need to compute these additional terms, which gives you a way of their distance to the remaining part of the network. So UI is defined as this value. As you can see, if UI is nothing but this term here, the distance of I to j. I don't know whether I'm going to combine them at this moment. So this is just another addition term to the other, just like distances to the other objects. And I divide this by n minus 2. That's what UI is. Uj is distance of y to distance of j to I and distance of j to other nodes, again divided by n minus 2. The good thing is that ui minus uj is this magical term that actually is the difference between x and y directly. Therefore, I can use it. Ui minus uj is x minus y. This was x plus y. If you add these two terms up, you get your 2x divided by 2, you get your x. So this is how x is defined. Okay, after you find x, y is simply x plus y was dij. If you subtract from it your x, you get yourself your y. Okay, so the remaining entity is now put into y. So this is these two formulas tell you how you find x and y. How you separate, how you divide that 7, the 7 between the distance of 7. Remember, it was between the nodes A and E. How do you divide that 7 between these two nodes? In UPGMA, it was 3.5 and 3.5. Here, we're going to see that it's going to be 1.5 and 5.5. So, and this will be due to the different UI UJs we're going to have. I'm just going to, in the remaining 15 minutes, I'm going to do the first iteration of the neighbor joining algorithm to see how it proceeds. And the remaining iterations are similar. We do the same thing. N is going to be changing, but we are going to compute UIs for all the objects in the from scratch, all for all the objects in our current matrix. This is used to update the matrix. This is used to set the edge weights on the tree. And this is just for updating the matrix. All right. And then let's see how it's going to work. And the final neighbor joining result is going to give us the actual tree. And and there are some phylogenetic tree resources on the web. Some of these links may be outdated, but you may just search for this Philip cluster legs. These are PhyML, some links that perform phylogenetic tree evolution. There's also, to draw the final constructed tree, there are tools to visualize the final constructed trees. But let's start with this. And as I said, I'm going to, as time permits, I may do more than one iteration. But let's start how we proceed with this neighbor joining algorithm given a matrix like this. Let me just again copy this part, get a new slide. And scale this quickly. All right, first thing is to compute those UIs. Let's start with that. Now, and the values we're going to get are not integer values you're going to see. First of all, here n is equal to 5, not a. N is equal to 5. So n minus 2 is 3. So for a, so UA is going to be equal to 10, 12, 8, 10, 12, 8, and 7. Okay? Those four numbers divided by 3, which is 37 divided by 3. So UA is 37 divided by 3. UB is 4, 4, 14, and 12. So the distance of B to C is, so B to C is not 12, sorry. B to C is 4. A to B is 10. So it's 10 plus 4, 4, 14. So B to A is 10. Then 4 and 4, CD, and 14. So if you look at this, is it 32? Yeah. It's 32 divided by 3. And UC, it is 16, 22, and 38. If I make any mistake, please just inform me. Okay, so let me do it again. 16, 6 makes 22, and 16, 38. And UD, let me just write UD here. UD is equal to 18 from here, 12 from here, so it's 30. 30 divided by 3, which is 10. But I will just leave them as divided by 3 to be able to compare them. UE, the final one, is this. So UE is really far away from the, E is really far away from the rest, right? It's going to be 49, right? 30, 40, 49. So 49 divided by 3 is, so I computed UI values. So these are the UIs. Now, the reason one of the reasons to compute those is not only to find 3 paths, but also to decide which pair of objects to combine. So I need to, I'm going to combine 2 objects. It may be UPGMA was deciding between BC and BD, right? In this case, for example, BC and BD is not a tie. If you look at this, if you look at these 3 objects, B, C, and D, although the distance between them, for example, the distance between BC is equal to the distance between BD, right? If you look at these UI values, minus UB minus UC, minus UB minus UC. Okay, UB is common in both of them, so not UC, UD. UB is common in both of them, so these parts are equal in these 2 things. But UC and UD are different. UC is 38 divided by 3, UD is 30 divided by 3, which means that since UC is larger, this one is going to be a smaller number. Okay, it's no longer a tie. For neighbor joining, combining B and C is more preferable compared to B and D. All right, so we should start with B and C in neighbor joining, but is this statement true? We may not be, right? We have to, why did we just look at BC and BD? For these measures, we need to look at all pairs of objects. For example, what about DAE minus UA minus UE? what if this one is smaller than this value here? Then I have to combine A and E in the first iteration instead of B and C. We should really do that. Actually, we should compare them. For example, this was 4. UB was minus 32 divided by 3, and UC was 38 divided by 3, minus 38 divided by 3, right? So this not divided by 2, 3. So this 4 is 12 divided by 3. I can write 4 as 12 divided by 3. So this will be minus 20 and minus 58 divided by 3. So if I'm not mistaken, so this is minus 58 divided by 3. So this measure here is minus 58 divided by 3. Now let's take a look at the same thing for A and E. AE is 7. I will write 7 as 21 divided by 3. And UA is 37 divided by 3. And UE is 49 divided by 3. So let's do the math. I'll just use my calculator. Yeah, there's no need to use calculator. So this is 70, this is 86, right? 86 minus 21, 67, no, 65. This is 65 divided, minus 65 divided by 3, right? Yeah, I'll use the calculator anyway. So let me use the calculator. 37 plus 49 minus 21. Yeah, it's 65. So you see, actually, this is a smaller number, which means that AE is more preferable. So we want this number, this measure, to be as small as possible because we want the distance, we want them to be close to each other, and we want them to be far away from the rest. So this measure, the smallest, the pair of objects for which this measure is smallest, we are going to choose those as the pair to combine. As you can see, 65 divided by 3 is smaller than 58 divided by 3. So I think this is the pair of objects to combine. But we cannot just decide by looking at only these 3 pairs. Okay, so the algorithm actually it has to look at all pairs of objects. What about, for example, combining A and B, A and C, A and D? But I just looked at these 3 because intuitively I think these were the most potential candidates. If you just, for example, if you replace if you look at A and B, the distance between them is large, and UA and UB is not that large anyway. So I think UA, I mean, we shouldn't just say I think. We have to look at all pairs of objects if you're doing it on the exam. But just to save some time, my guess, I will put my money on AE, and this is going to be the pair of objects. You may try the other pairs. As I said, you may take a look at AB, AC, AD. We already looked at BC, BD. There is also BE, CD, and the other one CE and DE. So we have to look at all these other pairs too. But as I said, I believe this one will have the smallest. If you look at these measures for these pairs, none of them is going to get a smaller value to us than this minus 65.3. So therefore, in this iteration, we choose to combine. In the first iteration, unlike UPGMA, A and E is a better candidate to combine in the first iteration. So we combine A and E. Now, we have to decide since we have this UA and UE values, 37 divided by 3, 49 divided by 3, I can find what this X and Y is by directly using that U, UI, UA, and UE. So in other words, this X will simply be equal to, this X is equal to the distance between A and E, which is 7, plus UA, which is 37 divided by 3, minus UE, which is 49 divided by 3, 49 divided by 3, divided by 2. This is what X is equal to. So what is this? Minus 12 divided by 3, right? 37, 49 minus 12 divided by 3 gives minus 4. 7 minus 4 is 3. 3 divided by 2 is equal to 1.5. So I found what X is equal to, which is 1.5 here, which is exactly the same thing here on this tree. So if 1.5 here is here, the remaining of that 7.5, I know that X plus Y is equal to 7. So therefore, the remaining 5.5 is going to go here. So this is how I used the UA and UE to also compute X and Y here. All right. So the final thing to do in this iteration is to update the matrix, which is this. I'm going to put AE here, AE, and B, C, D, B, C, D, B, C, D. So when we're updating this matrix, I need to find the distance of AE to B. So the distance of AE to B, if you look at this slide, you'll see that the way we compute it is we use the distance. So the distance of A to B and A to, so it's basically this distance of A to B plus distance of E to B minus the distance between A and E divided by 2. So the distance of AE to B is given like this, which means that this one, if you remember, this was X plus Z, this is Y plus Z, this is X plus Y. So if you subtract DE from it, you get the X and Y components from these distances by subtracting AE from here. The only remaining thing is Z components, and twice the Z components are here. So you divide by 2 to get your answer. So let's do that. What is the distance between A and B? 10. EB is 14. So 10, 14. 10 plus 14 minus 7 divided by 2. It's 24. So it's going to be 17, right? 24 minus 7 is 17 divided by 2, which is 8.5. So I will write here 8.5. So I have to compute the others, the distance of AE to C similarly. Distance of A to C plus distance of... by the way, in the other iterations, when we're computing this distance here between clusters, we do not refer to this original matrix. Your current matrix in that iteration is, what I mean is that in the second iteration, this will be our only reference point because AE is considered as a single object at the second iteration. This first matrix is only referred to in the initial first iteration. In the second iteration, when I'm computing, for example, UAE, UB, UC, UD, I will be doing the entire iteration on this single matrix. Okay, that's another important property of neighbor joining. But we have to compute these other remaining values by using similarly by using the paths on the tree. The path distances on the tree should be considered when computing the distances between clusters. The clusters are treated as single objects. It's not like average linkage clustering UPGMA applies. Okay, the cluster distances between clusters is found out by this highlighted formula that is here. It doesn't use average linkage clustering. It uses this formula to find the distance between clusters, which just uses the path distances on the tree. All right, so that's neighbor joining. As you can see, it's more time consuming. It takes more mathematical operations to perform at every iteration. All these UA, UB, UC, they are recomputed at every iteration for the new objects because number of objects is changed now. N is now 4. In the next iteration, we will be dividing not by 3, but by 2. All these values are going to be divided by 2. And then we are going to compute those UA values, and then we are going to again choose the one with the minimum value of this distance between them minus UI minus UJ. The pair which attains the minimum of these measures are going to be chosen as the pair to be combined in the following iteration. All right, so this concludes our chapter, phylogenetic trees. And I will be happy to answer your questions if you have any. And I will stop recording now. And on Thursday, we are going to continue with protein structures. And your third assignment is going to be on protein structures. So after we talk about protein structures for a week or so, I will then post your third assignment, which will be a programming assignment on protein structures. So it will just give you a way to have an experience with PDB files with those atomic coordinate values. All right, so but the phylogenetic trees discussion on phylogenetic trees is now complete. We will continue our lecture with protein structures on